This example will illustrate the methodology required to solve a mechanical problem with multiple objects connected together where one of them is exhibiting rolling motion. In this question, we have a uniform wheel of mass 12 kilograms and diameter 80 centimeters is being pulled up an incline by an attached mass, A, of 6 kilograms with a negligible mass pulley and string, so we don't need to consider the masses of the string or the pulley, and the string is wrapped around the wheel's edge as shown. We want to find the resulting acceleration of the hanging mass and of the rolling wheel, the tension in the connected cable, and the minimum coefficient of friction required to keep the wheel rolling without slipping. And that minimum coefficient of friction is going to be static friction because as the wheel rolls, the point of contact is at rest. The first step in any physical problem is to draw a diagram. The diagram has been given to us. And so step 2, we would normally label our positive directions for our vector components. In this example, we don't know which way the system moves, so we have to do that calculation first. And the way that it is done with an object that is exhibiting rolling motion is to analyze the moments on the wheel. So to answer this question, which way does the system move? We need to look at the rolling wheel itself. It is going to have, this is not quite a full free body diagram, I'm just looking at the torques on the wheel. It's going to have a tension exerted up the incline, and the component of its weight, which is mg sine theta, or mbg 3/5, that's going to be exerted down the incline, but at a different axis at its centroid. This wheel is going to be rolling around point P. And so these two forces are acting at two different distances. The centroid component of the weight that is exerted down the incline is 0.4 meters away from P, whereas the tension in the cable is 0.8 meters away from P, the full diameter of the wheel. And so the moment up the incline that's going to be approximately the tension in the cable times 0.8 meters. And so that's assuming here that I'm dealing with standard counterclockwise rotation. The tension in the cable pulling up the incline is at a distance of 0.8 meters from the axis of rotation, point P. We don't know what the tension in this cable is. But if it was in static equilibrium, the tension in that cable would be approximately equal to the weight of block A. Now, if the wheel goes up the incline, so that block A falls, this tension is going to be slightly less than that. If the wheel rolls down the incline and block A rises, the tension in the cable is going to be slightly more than this, but this is a reasonable first guess. And if we put in those numbers with mass A of 6 kilograms, we end up with a moment here of approximately, so 6 times 9.81 times 0.8, that's 47.088 Newton meters counterclockwise. If we compare this to the moment that is exerted down the incline by the weight vector acting at the centroid, the moment down the incline is approximately 3/5 mbg times the distance that force is from the axis of rotation, point P. And so if we put those numbers in, mass B is 12 kilograms. So 3/5 of 12 kilograms times 9.81 times 0.4, that's a total of about 28.2528 Newton meters. And that would be a clockwise rotation. These two moments are in opposite directions, but clearly this one is larger, almost by a factor of 2. So therefore we can make this conclusion that the wheel rolls up the incline and the block falls down. So now when we do step 2, where we label our positive directions, we now know that the block A is going to fall. So I'm going to label its acceleration A, lowercase a, as downward, and I'm going to choose the positive direction for my y-axis for that block to be down as well, to align the acceleration with my positive direction. And for the wheel, as it goes up the incline, because it's moving up the incline, I'm going to choose positive x up the incline and positive y perpendicular to the incline. The acceleration of that connected cable has to be the same as the acceleration of block A. And that's going to cause the wheel to roll in a counterclockwise direction, so I'm going to choose counterclockwise to be positive. So this is the first step. We calculate which direction the system is moving so that we can get our positive directions. Now that we know which way the system is moving, what we need to do is step 3, where we list our known and unknown quantities. And so we have that mass A, the mass of the block, was 6 kilograms. Mass B, the mass of the wheel, was 12 kilograms. The radius of the wheel was 0.4 meters. And because of the word uniform, we know it's a uniform disk. That tells us the moment of inertia around the centroid for the wheel is 1/2 mr squared. All right, so that's because it is a uniform wheel. We don't know the acceleration, and so remember what we're talking about. Just a quick little sketch here. We've got our wheel being pulled up the incline by that cable. That acceleration A is there. Acceleration A is here. And we've chosen those positive directions. We don't know the acceleration A, that's an unknown quantity. We're not going to know the acceleration of the center of wheel B, so that's also an unknown. We also don't know the tension in the cable. So the tension in the cable here and here are going to be the same number because we are ignoring the mass of the string and the pulley. And we're also going to need to know the coefficient of static friction on the rolling wheel. In order to find an equation that deals with these known and unknown quantities, we require a free body diagram and analyze it with Newton's second law. So I draw the free body diagram of block A. This one's going to be the easier of the two to analyze. Block A only has one thing in physical contact with it. The cable, which can only pull upward, and then it's going to have its weight, force due to gravity, MAG, acting down. If the acceleration is down and the positive y direction is down, when we analyze the free body diagram of block A, the equation that applies, step 4, would be net force equals mass times acceleration. Net force in the y direction is mass times acceleration in the y direction. You do the left-hand side of this expression independent of the right-hand side. Because down is positive, my weight vector is going to be a positive vector component. And tension will be a negative vector component. On the right-hand side, we put in the linear inertia, the mass of the object in this diagram, which happens to be specifically mass A. And the acceleration in the y direction happens to be unknown, but it is a positive quantity, unknown acceleration, positive A. Positive because it points in the same direction as positive. There are two unknowns in this expression, tension and acceleration. If I solve for acceleration, I end up dividing by mass. If I solve for tension, I only don't have to do any division. So it's actually easier to solve this equation for tension. Take that to the right-hand side. MAA goes to the left. I end up with tension is MAG minus MAA. So the tension in the cable is slightly less than the weight of the block, and that's going to allow the block to rise. So the maximum amount for the tension in that cable is going to be the weight of that block, which is about 60 newtons, 6 kilograms times 9.81. So we know the answer for the tension here is going to be less than about 60 newtons. If we go to the free body diagram of the wheel, this one's a little bit more complicated because we have an object, a rigid body that is exhibiting rotation, but it is rolling motion. So the object is physically connected to the cable. The cable is going to exert a cable force pulling tension acting at the top of the wheel, and the surface upon which this wheel rolls is going to exert two loads. A normal force on object B on the wheel, and also a force of friction. Now in this case, the force of friction is static friction, could be anywhere from 0 up to the coefficient of static friction times the normal force. We don't know what that number is. We also don't know exactly what direction it's going to be. If the tension's up the incline, that might have a tendency to cause the wheel to rotate, to want to spin and slide where this bottom surface moves down relative to the incline. So friction always opposes relative motion between surfaces, so it's likely that that force of friction is actually up the incline, that it's going to help pull the object up the incline. The weight vector of this object is directed straight down, but if we resolve it into its two components, the component that is along the incline is always mg sine theta, and because we have a 3-4 triangle, sine theta is 3/5. The component of the weight into the incline is mg cos theta, so that'll be 4/5 mbg. The distances that are involved here, from axis P, the point of contact, to the centroid is 0.4 meters, or the radius of object B. From the center up to where the cable tension is exerted, that's also a radius B, another 0.4 meters. In order to analyze the free body diagram of wheel B, we have some options. We can do net force in the x direction, but remember the acceleration of the object here is exerted or is determined at the cable connection point. And so that's an unknown quantity in the x direction. So is force of friction, and so is tension. That's three unknowns. So that's not really going to be useful when we have only a few equations to deal with. So to eliminate a lot of the unknowns, what I'm going to do is take moments around the point of contact. By taking the moments around axis P, it eliminates normal force and the 4/5 MBG component of the weight. Both of those lines of action pass through the axis and cause no spin. The force of friction line of action also passes through that axis and causes no spin. The only two forces that cause rotation around axis P are the cable tension and the weight vector down the incline. At the beginning of this question, those were the two competing forces that caused torque on the wheel. And so on the wheel, if I analyze the free body diagram of wheel B and do net moment about axis P is moment of inertia about axis P times angular acceleration. When we use the standard positive direction for rotation as counterclockwise, we have two components here. Tension acting at a distance of two radius b's from point P is going to give us positive rotation, and the 3/5 MBG is acting at 1 radius b. That's going to be a negative component. On the right-hand side of this expression, we have the moment of inertia around axis P. That, using the parallel axis theorem, is the moment of inertia around the centroid plus mass B times the distance from P to C. The centroid of that object at the center, and the distance from there to point P is a distance RB, the radius of that wheel. Alpha is the angular acceleration of the wheel. And we can relate this to the linear acceleration of the wheel if the object's cable is experiencing an unknown acceleration A. If we divide that by the radius to axis P, which happens to be 2RB, we will get angular acceleration. And so we end up with something like this: 2 tension RB minus 3/5 MBGRB equals moment of inertia around the center, because it's uniform, is 1/2 MBRB squared plus another MBRB squared is going to leave us with 3/2 MBRB squared inside. So that's actually 3/2 is exactly 3 times 1/2 MBRB squared. The object, a uniform wheel rolled upon its edge, is exactly 3 times as difficult to rotate around its edge than it is around its center of mass. And so I'm going to eventually solve this equation for tension. So if I write this, 2 tension RB equals 3/2 MBRB squared times A over 2RB plus 3/5 MBGRB. We can notice there's going to be some canceling going on. RB and one of the RB's cancel in the first term. And if I divide both sides of this expression by 2RB, we get 3/2 MBRBA plus 3/5 MBGRB, all divided by 2RB. The RB appears in all terms, and so it will cancel. And if I divide everything by 2, I end up with 3/4 MBA plus 3/10 MBG. This is the equation for tension from the wheel. We have an equation for tension from the block and an equation for tension from the wheel. We have 2 equations, 2 unknowns. If I set those 2 equations to be equivalent, we'll be able to solve for the only unknown in the question, the acceleration of the block A. And so if I set the tensions to be equal, the tension from looks like I've made an error here. 3/2 divided by 2 is 3/4. 3/4 divided by 2 is 3/8. Okay, so that should fix that up. The tension from the rolling wheel was 3/8 MBA plus 3/10 MBG. That's going to be equivalent to the tension from the block, which is MAG minus MAA. Only two of these terms have acceleration in them. If I move them both to the left and factor out the A, I'm left with 3/8 MB plus MA. And if I move everything else to the right side of the equation, I get MAG minus 3/10 MBG. And if I divide that expression by that mass-dependent statement, we find a relationship that calculates the acceleration of the system as MAG minus 3/10 MBG divided by 3/8 MB plus MA. Normally, whenever you do Newton's second law, you end up with an equation that talks about net force over net mass. And so if we have the net force to accelerate the system on the top, and then notice we get something that's related to net mass on the bottom. And because that cable is not connected at the centroid of the wheel, and because the object has to experience both linear and rotational motion, this is the equivalent factor for the resistance of that object to a change in its state of motion. If we plug in the numbers here, mass of A was 6 kilograms. G is 9.81 meters per second squared, minus 3/10 MB. MB was 12 kilograms times 9.81 meters per second squared, all over 3/8 of 12 kilograms plus 6 kilograms. We get kilogram meter per second squared on the top, kilograms on the bottom. If you calculate this out, you'll end up with 2.2423 meters per second squared, or to 3 significant digits, 2.24 meters per second squared. That acceleration applies to both block A that is falling, so that's 2.24 meters per second squared downward. And it also applies to the acceleration of the center of wheel B. But remember, the edge of the wheel experiences an acceleration of A, whereas the center of the wheel will have a lower acceleration because of its closer proximity to the axis of rotation. So if I take the acceleration that we just found and multiply it by this ratio, RB over 2RB, it'll end up being exactly half of its edge acceleration A. And so we end up with the acceleration of the wheel linearly, its center will be half of this. We end up with 1.12. meters per second squared, and that'll be up the incline of 3 on 4. So that answers part A. This answers part B. To calculate the tension in the cable, we can use either of the two equations we had at the beginning. So if I use tension is MAG minus MAA, that'll be 6 kilograms times 9.81 meters per second squared minus 2.24 meters per second squared. You'll end up with 45.4 newtons. You can also check this by using the other equation. If tension is 3/8 MBA plus 3/10 MBG, so that's 3/8 of 12 times 2.24 plus 3/10 of 12 times 9.81, you'll find that you also get a tension of 45.4 newtons. Okay, so getting the tension in the cable, you can always check it with either of these equations. In order to calculate the coefficient of friction, we need to calculate something to do with the force of friction that acts upon the wheel. And because we have rolling motion and linear motion on that free body diagram, so just as a reminder, remember the free body diagram of the wheel B looks something like this. We had our cable tension up the incline, we had our friction up the incline, we had the normal force perpendicular to the incline, and the weight vector resolved into two components, 3/5 MBG and 4/5 MBG. In order to analyze this equation, or this free body diagram, to calculate the force of friction, we have two choices. So on wheel B, I could do net moment around the centroid is moment of inertia of the centroid times the angular acceleration. And around the center of mass, if I take that as my axis of rotation, the tension is only acting at a distance of RB. But the force of friction is also acting at a distance, RB, from the centroid. But it's in the opposite direction, so it'll be a negative component. Moment of inertia around the centroid is 1/2 MBRB squared. And when we take moments around that centroid, notice the normal force and the 4/5 MBG components cancel out, as well as the 3/5 MBG. It has no distance to the axis of rotation. Angular acceleration, remember the edge of the wheel is traveling with acceleration A, so that'll be A over 2RB. We end up with RB canceling here and here. And if we divide both sides by RB, we're going to end up with 1/2 MB. RB will divide out on both sides and cancel. We get 1/2 MBA over 2. And so we get force of friction is tension minus 1/4 MBA. And with force of friction is tension minus 1/4 MBA. We will end up with 45.4 minus 1/4 of 12 kilograms times A. That solution for A there, remember, was 2.24 meters per second squared. We end up with a force of friction that is about 38 0.679 newtons. This is just an intermediate quantity here. I can check this by doing a completely independent analysis. If I do net force on this free body diagram, we have both tension and force of friction are up the incline, whereas the 3/5 mbg component is down the incline. The linear inertia of this object, when it's moving in a straight line, is the mass b, but we need to include the acceleration of the object, but we must include the acceleration of the centroid here only. So that's ab. Rearranging this equation for force of friction, I find we get mbab plus 3/5 mbg minus tension. And so the force of friction here will be 12 times, acceleration of b, remember, was only half. So 12 times 1.12 plus 3/5 of 12 times 9.81 minus the tension in the cable, which was 45.4 newtons. And if you multiply this out, you will get 38.679 newtons. So it's clear that the force of friction is the same. Remember, this is static friction. It is the force that is required in order to keep this thing moving in the specified direction without slipping, forcing it to roll. In order to calculate the coefficient of static friction, the force of friction should be the minimum force of friction will be the minimum static friction coefficient times the normal force. And if we compare here, we could do the analysis, but these two values for normal force and 4/5 MEG are the same. So the force of friction is the coefficient of static friction times 4/5 mbg. That will be the normal force. So the coefficient of static friction minimum, force of friction over 4/5 mbg. And if you put those numbers in,